Our most common battery systems today are Li-ion and lead-acid. But both systems have challenges and limitations that cry out for a better solution. The battery industry is littered with broken promises, but progress is being made. Storing electrical energy in an economical way remains one of our yet unresolved challenges in modern society. The saying goes, every 1% improvement in battery performance widens battery applications by 10%. A simple guideline reveals, the cost of energy doubles when stored in a battery for reuse. In terms of longevity, advancements are being made in the lithium-ion battery by using single crystal cathode material. Gaining longer life and holding higher capacity is driven by the electric vehicle industry that is striving for a 15-year battery life. However, as long as cell phones in the consumer market use common Li-ion types that are charged to the maximum allowable voltage, longevity will be short. In terms of specific energy, the silicon nanowire anode achieves high watt-hours per kilogram, watt-hour per kilogram, that can be twice that of commercial Li-ion cells, but nanowire-based structures have limited cycle life. Microscale C-islands form under the nanowire arrays with cycling that produces stress and cracking. The resulting capacity loss is caused by reduced contact with current collectors. Experimental batteries live mostly in sheltered laboratories and communicate to the outside world with promising but one-sided reports, often to entice investors. Some designs show unrealistic results with anticipated release dates that move with time. Most concepts disappear from the battery scene and die gracefully in the lab without anyone hearing of their passing. Few other products have similar stringent requirements as the battery, and the complexity puzzles venture capitalists who did well during the dot-com era and expect similar generous returns of their investment in only 3 years. Battery development typically takes 10 years. Most venture capitalists don't have the patience to wait and they pull back the money, leaving the developer in deep water. Raising capital is time-consuming and many startups devote as much time and energy for this task as to doing research. Most experimental batteries in the lithium family have one thing in common. They use a metallic lithium anode to achieve a higher specific energy than what is possible with the oxidized cathode in lithium-ion, the battery that is in common use today. Moly Energy was first to mass-produce a rechargeable Li metal battery in the 1980s, but it posed a serious safety risk as the growth of lithium dendrites caused electric shorts leading to thermal runaway conditions. The local fire department knew exactly where to go on a fire alarm at the Moly plant. It was the battery warehouse. After a venting event injured a battery user, all lithium metal packs were recalled in 1989. NEC and Tadiran tried to improve the design with limited success. Very few companies make rechargeable lithium metal batteries and most offer the primary versions only. Research continues and a possible solution with new materials as part of the solid-state lithium could be on hand. This design is described further in this section. Researchers have also developed an anode structure for Li-ion batteries that is based on silicon-carbon nanocomposite materials. A silicon anode could theoretically store 10 times the energy of a graphite anode, but expansions and shrinkage during charge and discharge make the system unstable. Adding graphite to the anode is said to achieve a theoretical capacity that is 5 times that of regular Li-ion with stable performance. However, the cycle life would be limited due to structural problems when inserting and extracting lithium-ion at high volume. Meeting the 8 basic requirements of the octagon battery is a challenge. Commercialization appears to dwell on a moving target that is always a decade ahead, but scientists are not giving up. Here are some of the most promising experimental batteries. Lithium-air, Li-air. Lithium-air provides an exciting new frontier because this battery promises to store far more energy than is possible with current lithium-ion technologies. Scientists borrowed the idea from zinc air and the fuel cell in making the battery, breathe air. The battery uses a catalytic air cathode that supplies oxygen, an electrolyte and a lithium anode. The theoretical specific energy of lithium-air is 13 kWh per kilogram. Aluminum-air is also being tried, and it is a bit lower at 8 kWh per kilogram. If these energies could indeed be delivered, metal-air, as the battery is also known, would be on par with gasoline at roughly 13 kWh per kilogram. But even if the end product were only 1/4 of the theoretical energy density, the electric motor with its better than 90% efficiency would make up for its lower capacity against the ice with a thermal efficiency of only 25 to 30%. Li-Air was proposed in the 1970s and gained renewed interest in the late 2000s, in part because of advancements in material science and the endeavor to find a better battery for the electric powertrain. Depending on the materials used, lithium-air produces voltages of between 1.7 and 3.2 volts cell. IBM, MIT, the University of California and other research centers are developing the technology. As with other air-breathing batteries, the specific power may be low, especially at cold temperatures. Air purity is also said to be a challenge as the air we breathe in our cities is not clean enough for lithium air and would need to be filtered. For all we know, the battery may end up with compressors, pumps and filters resembling a fuel cell, consuming 30% of its produced energy for auxiliary support to stay alive. Another problem is the sudden death syndrome. Lithium and oxygen form lithium peroxide films that produce a barrier, which prevents electron movement and results in an abrupt reduction in the battery's storage capacity. Scientists are experimenting with additives to prevent the film formation. The cycle life will also need to improve. Lab tests currently produce only 50 cycles. If you like the latest energy-saving technology and knowledge, please follow our channel. Lithium metal, Li metal. Lithium metal has long been seen as the future rechargeable battery because of its high specific energy and good loading capability. However, uncontrolled lithium deposition causes dendrite growth that induces safety hazards by penetrating the separator and producing an electrical short. After several failed attempts to commercialize rechargeable lithium metal batteries, research and limited manufacturing of this battery continues. In 2010, a trial lithium metal with a capacity of 300 watt-hours per kilogram was installed in an experimental electric vehicle. DBM Energy, the German manufacturer of this battery, claims 2,500 cycles, short charge times and competitive pricing if the battery were mass-produced. An Audi A2 with these batteries drove over 450 kilometers, 284 miles, from Munich to Berlin on a single charge. There is a rumor that the car destroyed itself by a fire while on a laboratory test. Although the lithium metal batteries passed the stringent approval tests, long-term safety remains an issue because metal filaments can form that might cause an electric short. At 300 watt-hours per kilogram, lithium metal has one of the highest specific energies of lithium-based rechargeable batteries. NCA in the Tesla S85 comes in at 250 watt-hours per kilogram. LMO in the BMW i3 has 120 watt-hours per kilogram and a similar chemistry in the Nissan Leaf has 80 watt-hours per kilogram. The BMW i3 and Leaf batteries are made for high durability. Tesla achieves this by oversizing. A solution to inhibit the growth of dendrite may be imminent. To produce dendrite-free deposits on Li metal batteries, tests are being conducted by adding nanodiamonds as an electrolyte additive. This works on the principle that lithium prefers to absorb onto the surface of a diamond, leading a uniform deposit and enhanced cycling performance. Tests have shown stable cycling for 200 hours, but this would not provide sufficient guarantee for consumer applications, such as mobile phones and laptops. In conjunction with the research work, Li-metal batteries may need other precautions including non-flammable electrolytes, safer electrode materials and stronger separators. Solid-state lithium. The current Li-ion uses a graphite anode and this reduces the specific energy. Solid-state technology replaces graphite with pure lithium and substitutes the liquid electrolyte soaked in a porous separator with a solid polymer or a ceramic separator. This resembles the 1970 lithium polymer that was discontinued due to safety and performance reasons. The solid-state battery shares similarity with lithium metal and scientists are trying to overcome the problem of metallic filament, dendrite, formation even with dry polymer and ceramic separators. Additional challenges are poor conductivity at cool temperatures, difficulty to diagnose problems within the cell and low cycle count. Solid-state prototypes are said to only reach 100 cycles. Solid-state batteries promise to store twice the energy compared to regular Li-ion, but the loading capabilities might be low, making them less suited for electric powertrains and applications requiring high currents. Targeted applications are load leveling for renewable energy source as well as EVs by cashing in on the short charge times that this battery allows. Research laboratories, including Bosch, predict that the solid-state battery might become commercially available by 2020 and be implemented in cars in 2025. Governments reward companies that do research on solid-state batteries with large grants. Lab reports boast high specific energy and superior safety by having no flammable electrolyte, but battery experts are not yet convinced on its viability to replace Li-ion. A renowned battery specialist says, "It is beyond my comprehension that a solid-state lithium battery can be made in a cost-effective way to compete with Li-ion using liquid electrolyte in terms of cost per kilowatt-hour, longevity and safety." Solid-state batteries tend to have high internal impedance, have poor low-temperature performance and are subject to dendrite growth. Lithium-sulfur, Li-S. By virtue of the low atomic weight of lithium and the moderate weight of sulfur, lithium-sulfur batteries offer a very high specific energy of 550 watt-hours per kilogram, about 3 times that of Li-ion. Li-S also has a respectable specific power of 2,500 Wh/kg. During discharge, lithium dissolves from the anode surface and reverses itself when charging by plating itself back onto the anode. Li-S has a cell voltage of 2.10 volts, offers good cold temperature discharge characteristics and can be recharged at -60 degrees Celsius, -76 degrees Fahrenheit. The battery is environmentally friendly. Sulfur, the main ingredient, is abundantly available. A price of $250 per kilowatt-hour is said to be possible. A typical Li-ion has a graphite anode that hosts lithium ions much like a hotel books guests. On discharge, the battery releases the ions to the cathode, replicating guests checking out in the morning. In Li-S, graphite is replaced by lithium metal, a catalyst that provides double duty as electrode and supplier of lithium ions. The Li-S battery gets rid of dead weight by replacing the metal oxide cathode used in a Li-ion with cheaper and lighter sulfur. Sulfur has the added advantage of double booking lithium atoms, something Li-ion cannot do. A challenge with lithium-sulfur is the limited cycle life of only 40 to 50 discharges as sulfur is lost during cycling by shuttling away from the cathode and reacting with the lithium anode. Test labs now report improvements by achieving 200 cycles. Other problems are poor conductivity, a degradation of the sulfur cathode with time and poor stability at higher temperatures. Since 2007, Stanford engineers have experimented with nanowire. Trials with graphene are also being done with promising results. Sodium ion, Na ion. Sodium ion represents a possible lower-cost alternative to Li-ion as sodium is inexpensive and readily available. Put aside in the late 1980s in favor of lithium, Na-ion has the advantage that it can be completely discharged without encountering stresses that are common with other battery systems. The battery can also be shipped without having to adhere to dangerous goods regulations. Some cells have 3.6 volts, and the specific energy is about 90 watt-hours per kilogram with a cost per kilowatt-hour that is similar to the lead-acid battery. Further development will be needed to improve the cycle count and solve the large volumetric expansion when the battery is fully charged. Lithium manganese iron phosphate, LMFP. Lithium manganese iron phosphate is said to increase the capacity by up to 15% over the regular Li-Phosphate LiFePO4 system. The average working voltage is 4.0 volts, specific energy is 135 watt-hours per kilogram and a cycle life is said to be 5,000. Economical cost and safety are other benefits, making this battery a candidate for the electric powertrain. Dry battery electrode. Maxwell Technology has developed the dry battery electrode that could increase the specific energy of Li-ion by 50% to 300 watt-hours per kilogram with potential to 500 watt-hours per kilogram at said cost savings in manufacturing. Maxwell borrows the dry coating method from manufacturing supercapacitors. Performance data have not yet been published. More information should become available as Tesla, Inc. has purchased Maxwell. If you like the latest energy-saving technology and knowledge, please follow our channel.